Welcome to Brain Vision.
So we're told that at a construction site, a 65-kilogram bucket of concrete hangs from a light but strong cable that passes over a light friction-free pulley and is connected to an 80-kilogram box on a horizontal roof. So we have a picture of it, and I'll draw a little free body diagram of the whole situation here, where I've lumped the bag of gravel that also sits on top of the box, and that's a 50-kilogram bag of gravel. And so we've lumped it all together, so we have a normal force between the box and gravel system and the roof, friction force acting to keep this from moving, the weight of the bucket of concrete acting to pull it this way, and then obviously its mass, the total mass of the gravel and the box times G. And so what we get from this free body diagram, and we're going to assume that it's in equilibrium. Obviously we pretty sure that it's in equilibrium vertically, but again, we're not sure if the friction force is great enough to keep this from sliding. But we can make that assumption and then check if it's valid afterwards. So we have N equals the total mass, which is 130 kilograms, times G. And then F, we can figure out is equal to M1G, and that becomes 60 times G. And if we look at what the static coefficient of friction times the normal force is, that becomes 91 G. And we can see that in fact this friction force is less than the maximum value that it can be to prevent it from sliding. So it is in static equilibrium. We're also asked what the friction force between the box and the gravel is. And we can draw free body diagrams like this, and we basically find out that this friction force is 0. Because this is static and there's nothing trying to slide this off. If this were a dynamic system, then we'd have to worry about the box sliding out from under the gravel. So in the second part of the problem, we are asked if suddenly a worker picks up the bag of gravel, use the energy conservation to find the speed of the bucket after it has descended 2 meters from rest. And I'll let you guys check the answer by solving this problem using Newton's laws. But that's again just drawing free body diagrams. But if you use work, we know that the rate of work done, or the rate of work in the system must equal the rate of energy change in the system must equal the rate of work done on the system. And that rate of work done is from the friction force. So here's the friction force and times the velocity. So this is the power being dissipated from the rate of friction. And then it's a negative because it's taking energy out. So we can integrate this. And so we get E equals, and since this guy is constant in time, then V just becomes X, which is the distance the box has traveled, and then plus some constant of integration. And so then we can say that, well, this constant of integration, if we measure everything from where measure the height of the concrete bucket, or the bucket of concrete from where it starts at rest, then this guy gets to be 0 because everything starts at rest and the potential energy is 0 from our reference point. And so then this must be, N is M2G. This is the mass of the box. And then we have the kinetic energy later on. So then the kinetic energy at the time when the bucket has dropped 2 meters, we have the kinetic energy of the box kinetic energy of the bucket, and then the change in potential energy in the bucket. Now, because the cable is inextensible, we can assume that x equals y, so that the distance that the box moves has to be the same distance that the bucket falls. So we have our equation here, and we can do some rearranging, and we get that 1/2 the total mass of the bucket and the box times the velocity squared equals minus the friction force times the displacement plus the gravitational energy that was it was removed from the system, but it caused the velocity to increase. And so if we solve for y dot, we simply get y dot equals 2.99 meters per second.